Differential and integral operations 11. The continuity equation for a fluid is divergence of J plus del rho del T equals 0, where J is rho times vector V. Show divergence of V is 0 if the fluid is incompressible, constant density, and part B, apply Gauss theorem to the continuity equation and interpret the result. Now this rho is the density of the fluid and V is the flow velocity in this equation, and J is the particle flux in the continuity equation, and we are given that divergence of J, the particle flux, plus del rho del T is equal to 0. That's the continuity equation. But for an incompressible liquid with constant density, del rho del T is equal to 0 for an incompressible fluid. All right. And this implies that divergence of J which is divergence of the density multiplied with the flow velocity, which is the density, because density is a constant, multiplied by divergence of the flow velocity is 0. Therefore, divergence of the flow velocity is 0. So that's the answer to part A. Show that the divergence of B is 0. Now apply Gauss theorem to the continuity equation and interpret the result. Now we have divergence of J is equal to minus time derivative of the density del rho del T. If I apply Gauss theorem, the volume integral divergence of J d tau is equal to minus the volume integral del rho del T d tau. Okay. According to Gauss theorem, this is the closed surface integral d sigma dot J, which is minus volume integral del rho del T d tau. So this is basically Gauss theorem. All right. So what does it say? The net flux of a fluid through a closed surface S is equal to minus the rate of change, equal to minus the rate of change of density integrated over the volume V bounded by the closed surface S. For example, this is our volume B, which is bounded by a closed surface S. So a net flow into or out of the volume B through surface S implies a change of density. This implies a change of density in that volume. So we must have a change of density in this volume so that we will get a net flow through this surface into the surface or out of the surface that is basically at the boundary of this volume V. So that's what it means. All right, so here we are given the continuity equation, divergence of the particle flux plus the time derivative of the density is equal to 0, and J is equal to rho times the fluid flow velocity V, and del rho del T is equal to 0 for an incompressible liquid, which means divergence of V is 0. Why? Because divergence of rho V, which is rho times divergence of V, must be 0. This term is 0. That's what we find in part A. In part B, if I take the volume integral divergence of J d tau, this gives me the volume integral minus volume integral del rho del T d tau. That's Gauss theorem. The net flux of the fluid through a closed surface S is equal to minus the rate of change of the density integrated over the volume bounded by the closed surface S. So this actually whole surface S. If there is a net flow into or out of this volume V, if this is non-zero, that implies that there must be a change of density in that volume, a time-dependent density in that volume for this to occur.